Here we build a rectangular enclosure which is against the wall with 100 feet of fencing. Let x represent the length of each of the two sides which touches the wall, and y represents the length of the side which is parallel to the wall. And in this situation, we have to determine the side lengths so that the area is maximum. So let's see how to determine that. So this is an optimization problem where we have to optimize the area with the constraint fencing. So basically we have to need two equation, one for the constraint and the other one is the optimization equation. We create the constraint equation using the fencing information, and we have to optimize the area. So we create this optimization equation using the area information. So first, let's create the constraint equation using the fencing. We are told that it requires 100 feet of fencing to construct this rectangular enclosure. The fencing is basically the perimeter of the rectangular wall. So if you go around this rectangular enclosure, not including the wall, we see that this one is x, this one is y, and this one is x. So we have to add all these to get the fencing equation. So therefore, we write fencing of the rectangular enclosure. This equals x plus y plus x. So here we combine these two. These two are like terms. X plus x is 2x plus y. And we are already given that it requires about 100 feet of fencing. So this equals 100. Let's see that this constraint equation is 2x plus y equals 100. This be equation number 1. Now we have to create the optimization equation using the area information. So let's write down the area of the rectangular enclosure. Area equals length times width. We see that length is y and width is x. So we can say that it is y times x, or otherwise we can also write down this as x times y. Now we need this area equation in terms of one variable. So we have to replace this y using the constraint equation. So first let's find out y from this constraint equation. We have 2x plus y equals 100. Subtracting 2x from both sides, we get y equals 100 minus 2x. And so therefore we can now write down this area. uh, we represent area by a, and this equals x times of y, which equals 100 minus 2x. Now let's distribute the x so that we can write down this area in terms of function notation, that is a of x. This equals x times 100 is 100x, and then x times negative 2x is negative 2x squared. So this is the optimization equation, a of x. Now to optimize this area, we need the first derivative. That is, we have to set up a prime of x equals 0. This a prime of x represents the first derivative of the area function. So let's find the derivative of this area function, which is a prime of x. And this equals the derivative of 100x is 100 times the derivative of x is 1 minus the derivative of 2x squared. We write 2, and then using the power rule of differentiation, the derivative of x squared is 2x. Let's simplify this. We have a prime of x, and this equals 100 minus 2 times 2x is 4x. Now we need to replace a prime of x equals 0. So let's do that. This gives 0 equals 100 minus 4x. Solving for x, we get 4x equals 100, and so x equals 100 divided by 4 equals 25. So this is basically the critical point of the area function. Now we have to verify if at this critical point this area is maximum. So for that we are going to use the second derivative. So let's find the second derivative of the area function, and this equals 100 times. I'm going to use this 1 because this is the first derivative, and to find the second derivative we utilize this. So here we have the derivative 100 is 0 minus this one is negative 4x, which is negative 4 times the derivative of x is 1. So this one is basically negative, that is negative 4, and this is always less than 0 irrespective of if you replace x into this one. As such, it is independent of x. We don't have option to replace the x over here, which means this negative 4 is always less than 0. And so we see that according to the second derivative test, when the area function is less than 0, the area is maximum. Maximum. So thus we have verified that when x equal to 25, the area is maximum. And this means we can now find the y. So we find the y using the constraint equation, or we can use this equation y equals 100 minus 2x. So let's use 100 minus 2x. We now replace x by 25, and so this gives 100 minus 2 times of 25, and so this equals 100 minus 2 times 25 is 50, and this gives 50. So we found that y equals 50. We can also find the corresponding area. So let's use the area equation, which is 100x minus 2x squared, or otherwise we can use this equation. This one is simple. Since we have determined the y as well, we can determine the area using the equation x times y. And so this gives x is 25 and y is 50, and this equals 25 times 50 is 1250. So therefore let's write down the sides. X equals 25 feet, y equals 50 feet, and area equals 1250, and this is in feet square.